So we left off last time, we were talking about basically statements, logical statements that we can make. In this case, we can talk about making a statement, have a variable applied to it, P and Q and R and S and T, whatever you want to call your variables. And that's just to make it simple. And if you put a tilde symbol in front, you're saying the negation of that, not that statement. Well, there's some other kinds of ways we can make statements. We can talk specifically about quantified statements. These are exactly what they sound like. They talk about quantities of things. They don't have to be specific quantities like there are exactly 37 apples in this box. It doesn't have to be that specific, but we're going to use the words all, some, no, none, things like that to really discuss or to introduce these concepts. So for instance, all poets are writers. You're making a quantified statement because you're basically talking about a number of things. Anything that is a poet, any person rather that is a poet is a writer. That's what you're saying there. Also, you can say all these things and they don't have to be true statements. Remember, we're just talking about them in general, about statements. We will assess the truth of a statement in the next section, really, and especially in section 3. So all poets are writers. Some people are bigots. No math books have pictures. Some students do not work hard. These are all examples of quantified statements. Now, these are kind of written in the, the main way. All A are B. So we're going to talk about just general categories. All A are B, some A are B, no A are B, some A are not B. But there's actually an equivalent way that we can rewrite some of these statements. In fact, there might be several equivalent ways. If you get fancy with the English language, you can use all kinds of fancy words, but you have to be able to break down the basic logic of what is being said. So if you have the statement, all A are B, that's actually equivalent to kind of a double negative here. There are no A that are not B. The no and the not kind of are double negatives. And that makes sense. Think about the statement, all poets are writers. Isn't that the exact same as saying there are no poets which are not writers? Yeah, if there's no poets that are not writers, then all poets must be writers, just by definition. You're not allowing for a single poet to exist who is not also a writer. Thus, you're saying all poets are writers. Riders on the Storm. It's an old song. Probably have not heard of it. That's okay. Yeah, they're by this band. You've probably never heard of them. I'm just kidding. It's an old hipster joke. Anyways, the next principal statement is that some things in category A are also in category B. Some A are B. Well, an equivalent way to express that statement, when you say some, you're actually saying at least one. You're saying at least one of category A is also in category B. Thus, you're saying there exists at least one A that is B, that is a B. So for instance, the statement, some people are bigots, the only way that could be possible, a logically equivalent way to say that, in other words, is that at least one person is a bigot. Now, it could be that all people are bigots, but you're not saying all of them, you're just saying at least one is a bigot. And I would doubt that everybody is a bigot, but, I don't know everything. Next up, no A or B. You're saying that nothing which belongs in category A can be in category B. Whether or not that's a true statement, if you make that statement, that's equivalent to saying all things in category A are not members of category B. It just kind of makes sense. No common colds are fatal. Now that may not actually be true, so we're not concerned with the truth of that statement. No common colds are fatal. That must be the same as saying that every common cold on the planet is not fatal. You're kind of just switching around where you're saying the word no. It's really all you're doing at the end of the day. And then finally, some A are not B. There's at least one element, there's at least one thing in this category A, which is not also in category B. That's equivalent to saying that not all things in category A are also in category B. Some students do not work hard is equivalent to saying that not all students work hard. If you have some students that do not work hard, you have at least one student that does not work hard. Thus, not all the students work hard. It's a neat little table. I think the toughest one is to realize that the word some just means at least one. You may not always think about it like that. That is logically what you're saying. What's also interesting is that if it happened to be the case that all poets were writers, you could also say some poets are writers, and logically speaking, you're not wrong. Because it just says at least one. It doesn't say that you have to throw out the possibility that all of them are. So all and some, they're not used interchangeably, but if you can say all, you can actually say some as well and also create a true statement. It's kind of weird that way by strict definition. Usually when you use the word some, you don't want to go all the way up and say all of them are. But in logic, you can. So sometimes logic, the rules are perhaps a little bit more specific than we might use in regular English, but that's okay. Now, if you want to take the negations of quantified statements, you have the four basic statement types. All A are B, no A are B, some A are B, some A are not B. The negation of the statement, all A are B. You might think, okay, well, for instance, the statement, all poets are writers. If I wanted to try and negate that or counteract it, the opposite stance you'd think is that no poets are writers. But that's actually not true. All poets are writers. You can disprove that statement. You can negate it by simply finding one poet who's not a writer. Thus, the negation is that there's at least one, some poet that is not a writer. So the negation of everything is to just find at least one that is not that. It doesn't mean they're all not that. And that's kind of a little bit subtle. That's something you wouldn't expect. You would expect all A are B's negation to be that no A are B. But that's not the case. And so part of it is, yeah, maybe you could argue that some of this is memory, but it's really not when you think about the logic underneath the surface. That's what we're really trying to get at. So the statement, all writers are poets here, let's zoom in. Zoomify. Oh. All writers are poets. That means that the category of writers is entirely wrapped inside the category of being a poet, if you were to say that. You notice then that's also similar to the subset. Remember, that means writers, the set of writers is a subset of the set of poets. The negation of that, though, is to find a single writer who is not a poet. That's going to be this space here. So this is stuff that kind of takes a little while to sink in. It's not an overnight, rousing success. You have to kind of think about it a little bit. So let's look at an example. A mechanic told me all piston rings were replaced. Maybe the mechanic has been working in your car. However, it turns out the mechanic is always lying. Everything that comes out of the mechanic's mouth is a lie. So if the mechanic tells you all piston rings were replaced, you need to say, well, the truth is actually the negation of that. The truth is the opposite of what the mechanic said, because the mechanic always lies. And so the opposite of all piston rings were replaced is not to say no piston rings were replaced. The mechanic is lying as long as there is at least one piston ring that was not replaced. So the opposite of all is not none. The opposite of all is there's at least one that is not. And so if the mechanic says, all piston rings were replaced, but the mechanic's lying, then the truth of the matter is that some piston rings in the car were not replaced. How do you know that? Well, just think about it logically. If you can't think about it logically, you could think about the 4 basic quantifiable statements you can make. If you go deeper and you study deeper into logic, these are actually 4 of our well-formed formulas, we call them. And they are actually, there's going to be certain things called syllogisms that we're going to take a brief look at, which are nothing more than an interconnected series of logical statements consisting of hypotheses and at least one conclusion. And what we try to do is we try to say, is the conclusion true based on the hypotheses? Can we deduce that conclusion from the hypotheses? And so these are well-formed formulas. These are 4 of the basic 8 well-formed formulas that exist. But it's useful. At first you might need to memorize it, but as you go down the rabbit's hole, it'll become more and more useful for you to just really think through the problem. What does it mean for it to be the opposite of some A or B? Things like that. Okay, we're rocking, we're rolling. We've got some of the basic ideas of negations out of the way. But we need to continue on further down the rabbit hole. We're going to talk about compound statements and connectives is what we're going to call them. Now, the thing is, we just barely touch logic in this course, but it's nice. It's nice that we get a nice introduction to logic, because logic is fun. Logic is so much fun to just sit and think about the statement someone makes and see what you can deduce from that statement, and also to see what the negations of those statements are. You can decide if an argument is sound. In fact, in more broader logic, we refer to an argument as valid only if the conclusion can be logically deduced from the hypotheses, and we assume the hypotheses to be true. So to be logically valid, all you have to do is draw a correct conclusion, assuming the supporting evidence is all true. An argument, though, is logically sound if it is not only logically valid, not only that the conclusion can be logically drawn from the hypotheses, but also if the hypotheses happen to be true as well. And as you can imagine, there are objective ways that you can determine the logical validity of an argument, but it's a lot harder. There's still ways, but it's harder to determine the logical soundness of an argument. So this is kind of interesting. And all kinds of examples abound. Let me find a good example of a syllogism. I could make one up, but I think it'd be cooler if we went to an online resource here. Let's see, let me find a good example of a syllogism. Okay, a very simple one. A very simple one might just be all mammals are animals. All elephants are mammals. Thus, all elephants are animals. Actually, I'll go even better than that. Let me change the color of the last thing here. This is going to be the conclusion. In logic, we use this little 3-dot triangle kind of thing. It means therefore or thus. This is an example of a syllogism. You see the word kind of logic, logi, is embedded in there. A syllogism is nothing more than an interconnected series of statements. And to be a true syllogism, you really have to have hypotheses, your supporting evidence, and at least one conclusion. The conclusion is what you're drawing from the hypotheses. And if you write things in proper order, you don't have to, but you'll usually want your hypotheses to come first. And then you're going to want your conclusion to come last. Or conclusions. You could draw multiple conclusions. Now, what we're doing in logic is this. What we're ultimately going to be doing. Look at this statement. All elephants are animals. That's a true statement, isn't it? Sure, unless you don't have to get weird and say, what about toy elephants? But when we're talking about elephants, we're clearly talking about living elephants. So this by itself is a true statement as it's written, and you can completely ignore the hypotheses. This is a true statement, but whenever you bring the hypotheses in, suddenly we're not talking about just evaluating the conclusion on its own merits. We are trying to make sure that the conclusion logically follows from the hypotheses. If it doesn't mean the conclusion is false in general. It just means that this is a bad argument. All you're saying is, well, okay, your conclusion is true, but not for the reasons you're saying. So this entire argument can be true or false. It doesn't mean the conclusion is true or false. That's the point of logical deduction. Logical deduction attempts to draw conclusions based on hypotheses that are given. So let's see. All mammals are animals. All elephants are mammals. Therefore, all elephants are animals. Let's draw a quick picture of this. The first statement, all mammals are animals. Okay, so that means of this circle here, that consists of animals. Within that circle, and all I'm doing is translating this first statement here. Within that circle, then, must exist the set of mammals. I'm not saying even if that's a true statement or not. Now, I think you and I would agree it is a true statement, but I'm not saying it's true. All I'm saying is this is a visual representation of this first hypothesis here. The next line says all elephants are mammals. Well, we've already drawn a circle for mammals. If this second statement, if we wanted to interpret it visually, we could then draw another circle within the mammals circle and call that the set of all elephants. And now let's see if, based on this picture we were able to make, if this is a true statement. Oh, it is, because all elephants are animals, your conclusion. Well, look, the circle of elephants is entirely inside the circle of animals. There's another circle that's inside as well, but it's also in the circle of all animals. So This is a valid argument because the conclusion logically follows from the hypotheses. That's it. That also doesn't mean the conclusion is true. It just means that if we assumed the hypotheses to be true, the conclusion is true. That's what it takes to be a valid argument. It's simply, I could put any statements I want, even statements that are clearly nonsense. But as long as I draw a logically valid conclusion from them, I've made a valid argument, but it's better to make a sound argument. A sound argument actually looks at those hypotheses and makes sure they're correct. And there are procedures for doing that. In this case, it's a little bit of common sense procedure. This first hypothesis, all mammals are animals. Yeah, that seems to be a true statement. So separately, what I can do is I can put a stamp. I can put my stamp of approval there. That seems to be a true statement. Yeah. The next statement, all elephants are mammals. Sure, they fit the definition of a mammal. I mean, this is just by definition, pretty much. This isn't even debatable, really. So not only did the conclusion logically follow from these hypotheses, it also happens these hypotheses are true. And because they're true, we've also made a sound argument. And a sound argument is great. A sound argument means we've not only drawn a proper conclusion, the conclusion is true also because the hypotheses were true. This is also a sound argument because it is already a valid argument. We've already determined that. And the hypotheses are true. So not only is it valid, it's also sound. And it's better to be a sound argument, I think. Well, not only I think, it clearly is better to be a sound argument. So that's kind of interesting. Let's take this example one step further. So we've made a sound argument. Even without these hypotheses, we can tell the conclusion is true. But it's nice to know we drew proper conclusions from these hypotheses. But now let's mess it up a little bit. Let's see if I can. Let's see what I can do here. Let me think about this one. All mammals are elephants. All elephants, or rather, all animals are mammals. Therefore, all elephants are animals. Now, you'll notice very quickly that both of these hypotheses are false. They're terrible hypotheses. All mammals are elephants? No, they're not. Human beings are mammals and we're not elephants. You know, anything. Your cat is a mammal and it's clearly not an elephant. But let's do this. Let's draw the picture for what the hypotheses are saying. In the picture, well, if we use the circle ideas again, let's make it as big as we can. All mammals are elephants. So that means the set of elephants is the outermost, and then the set of mammals has to fall into that. The next statement, all animals are mammals, well, that means the set of all animals has to fall inside the set of mammals. So this is the picture that's drawn from these hypotheses. It's wrong. It is way wrong. But now look, the conclusion, all elephants are animals. Well, no, this picture does not support that conclusion at all. Look, there are things like maybe something that's right here. Maybe this thing right here, Johnny the elephant. Johnny the elephant could exist out here, but not be a mammal or even an animal according to just these hypotheses. So it actually has nothing to do with the fact that the hypotheses are wrong. We can't even draw the correct conclusion from this. This is an invalid argument. We cannot draw the conclusion from those hypotheses, even if the hypotheses were correct, which they're not. Because you can have something, according to this picture, you can have something that's an elephant, but is not an animal, because it's outside the animal circle, but still in the elephant circle. So it's clearly not a valid argument. It's also not a sound argument, because a sound argument has to be valid to begin with. Well, that also means then that you would think, well, then the conclusion must be wrong. All elephants are animals must be a wrong statement, but it's not. We can tell just independently that that's a correct statement. So we're not saying the conclusion is incorrect. We're saying the argument we're using to support that conclusion is incorrect. It's invalid. So this is the kind of stuff that I kind of find interesting. And now we're not quite going to go into as much detail about that in this section as I'd like. I'd like to go into much more detail, but that's not always going to be the case. So we need to talk about simple versus compound statements. Simple statements just convey a single idea. They don't have any connective words or connecting words. Compound statements, though, may consist of simpler statements and use connectives in order to bring those statements together. So a compound statement is still a statement. It's kind of constructed of other simpler, more simple statements. The major connectives that we're going to use are and, the word or, and recall, in logic/math, the word or really translates to and/or in English, the way you'd use and or in English. But we just call it or. You can also use connectives if, then, and then you put the meat of the argument in the middle there. Also if and only if. Also, other terms that might be logically equivalent to those connectives are also those connectives. So, and statements are really interesting. If you're starting with two simple statements, P and Q. Now, P and Q don't have to be simple in general. You could have a statement P that it has multiple connectives already in it. But when they are simple, the compound statement P and Q can be symbolized P, and then what looks like a triangle missing its bottom, its base, P and Q. This symbol here, this upside down V, is literally the word and when you're talking about logic here. It's literally the word and. So what we'll do is we'll call this a conjunction. We're conjuncting the two statements. We're kind of bringing them together. That's really all there is to say about that there, Pilgrim. Now it's interesting. Let's say we have the statement, P is the statement, it is after 5 p.m. And it is just referring to the time. What is time? Well, that's a better question. It's a tough question to answer. Q is the statement, they are working. So if you wanted to make this, the symbolic form of P and Q is P, this thing, this upside down V, and Q. So this P and Q translates to English, it's after 5 p.m. and they're working. There's other ways to say it's after 5 p.m., but they're working. The word but, B-U-T, actually translates to the word and. It's just when you say but, you usually have some kind of I don't know, shock value or surprising element. It's a persuasive strategy actually, but it just logically translates to the word and. If you wanted to make the statement P and not Q, remember the order of operations, or perhaps we haven't talked so much about it, but the order of operations is going to put the negation first. You negate Q first, according to this, then you do P and this part. So if you want to say it's after 5 p.m. and they're not working, you'd say P and not Q, no parentheses needed. No parentheses needed. There's a couple different words we can use for the word and in the English language, and you may not have realized, but logically it just translates to the word and. P and Q, of course, P but Q, P yet Q, P nevertheless Q, P however Q. You don't realize it, but you're saying that while this first thing is true, also this second thing is the case. Or at least that's what you're saying, even if you're full of nonsense and don't know what you're talking about, or just lying, you're still making that kind of statement. Of course, in the English language, we would use the word but to kind of provide, I wouldn't call it a shock, but it does make it like, oh, that's unexpected or something like that. It has a little bit of a rhetorical value. There's a strategy behind it. Now, this one is tough, the word or. When you think of the word or in regular English, I visited London or Paris. I don't know why you'd ever say that, but maybe if you wanted to get someone to guess where you went for your vacation, well, no one's going to London or Paris during COVID, I think, but maybe you could. If you wanted someone to guess where you went, I visited London or Paris. Technically, what you probably intend to say is that you visited one or the other. You either visited London or you visited Paris, but not both of them. That's called the exclusive or. That's usually what you mean when you say that. But in math and in logic, that's not going to be what the word or means. In math/logic, or is the inclusive or, the one that's down here. Technically, in math and logic, if you make the statement, I visited London or Paris, you could be saying that you visited one or the other, or that you visited both. You could be saying all three of those possibilities. Why do we do that? Well, think about it. If I don't clarify, it could be either one of these. It could be the exclusive or it could be the inclusive or. If I'm not exact in what I'm saying, these actually could be two slightly different statements. So we have just decided as a convention in mathematics that the word or means and/or. And there's a good reason for it. It's because the word or is going to be attached to the union from set theory. That's why we do it, really, because we defined the union to be that way. So one of them got defined, the other one just kind of adjusted around it. Which brings up a great point. Everything we learned about in chapter 2, the set theory business, remember we learned about, what do we call it? The complement. We learned about taking the complement of a set. We learned about taking the union of a set, the intersection of a set. All of those have direct analogs in logic. In logic, the word or here is the union from set theory. In logic, the word and is the exact same as the intersection from set theory. We may not be calling these sets of things, but they secretly are. They secretly are. The negation is going to be the complement from set theory. And then what we're going to learn later, the if-then statement is actually a subset, is actually related to our subset concept. The if and only if is a two-way subset, where two things are subsets of each other, meaning they're the same set. So lots of interesting kind of implications from this. So when we use the word or in math or logic, we are talking about this one, the inclusive. So we call that, another word we use for it is the disjunction. The disjunction, instead of the conjunction, the disjunction. It sounds like a train stop where you just get insulted. Welcome to the disjunction. You look bad today. You look really bad today. You know, that's the disjunction. You get off the train, people are mean to you. And that's, you know, that joke is a little bit of a stretch. It's not my best joke. Or perhaps it is, and I'm just not very funny. But that's not going to be the case. We're not going to let that be the case. Instead of using an upside down V like we did for the and statement, the conjunction, we're going to use a regular old V, but it's not the letter V. It's a symbol that looks like V, but it's its own separate symbol. So if you have two statements, P and Q, and they are, this bill receives majority approval in the Senate, and another statement, Q, this bill becomes a law. Well, if you wanted to say this bill receives majority approval or it becomes a law, you'd use P, the V symbol, and Q. You're saying P or Q. If you want to say the bill receives a majority approval or the bill does not become a law, you're saying P or not Q. Using a little bit of logic. Now, what's really interesting are the if-then statements. If you're saying that all poets are writers, well, then if you're a poet, you must be a writer, if that's your statement here. And let's just assume the statement to be true. All poets are writers. So if you are in the set of poets, you're also in the set of writers. So that's actually the subset, if you think about it. All poets are writers. Another way to say that then is if a person is a poet, then that person is a writer. It's exactly the same. So quantified statements can just be turned into if-then statements. Some quantified statements can. These are all three logically equivalent ways of writing out the idea that all poets are writers. But we're going to graduate and use the if-then statement. Now, there's nothing that says this has to be true. We're just saying this is a visual representation of the statement, of the idea that's being presented in this statement. But it doesn't mean it's true. You could consider someone who just makes music a poet, although arguably they have to write down their lyrics or they've written them in their head or something like that. So you could still argue that musicians are writers as well. Even if all they do is make acoustic music, they're still writing. In a way, they're writing their lyric or their chords and all that, whatever, the melody. If you want to make an if-then statement, if the statement P, then the statement Q, you use an arrow, which is absolutely a great symbol for it because you're saying that this statement P points to the statement Q. If this statement P is true, then the statement Q is the case. Now, that entire statement might itself be false, but you're just using the arrow to point at it. This is called a conditional statement because you're putting a condition on Q that P must be the case in a way. Or actually, no, excuse me, you're doing it the other way around, technically. You're saying that for P to be true, Q must be the case, which sounds a little weird, but it is how that works. The statement before the arrow, the if portion, is called the antecedent. The statement after the arrow is not called the unclecedent. That would have been just too perfect. They call that the consequent. Antecedent, when are we going outside? I don't know why I said that. But you know, the word aunt, that's not the word aunt, that's ante, which is like before, prior to. Anywho, I mean, we're not going to use the term antecedent consequence so much, but it's just kind of interesting to know. But we will call it the conditional statement. We do need to know about the arrow notation for this. So if you want to if you have statements P and Q, P is the statement A person is a father, or this person perhaps is a father. Q is the statement, a person is male. If you wanted to write out the statement, if a person is a father, then they are a male, you would just say P pointing to Q. And you would literally read that, even though ifs and thens aren't written here, you would literally read this if P then Q. If P then Q. That's not to say that if P, that's not to say this is a true statement. Again, we're not ready to evaluate the truth of these matters just yet. We're simply symbolizing these statements. We're just finding ways to write them out in symbol form. If you wanted to, using the same P and Q, P is the statement a person's a father, Q is the statement a person is male. If you wanted to write the statement, if a person is not male, then that person is not a father, you would have to use negations, the tildes, and actually the male part comes first, then the part about being a father comes second. So that would be symbolized not if not Q, then not P. So it's kind of interesting. No parentheses are needed because we already know that this tilde Q only applies to the Q and nothing else. You can actually write a statement like this. You can use the tilde, or you know what, I'll just use a text box. You can use the tilde, and then you could actually put this in there. And that actually means something else. This statement here with the parentheses is not the same as this statement. Because by putting this in parentheses, you need to take the if Q, then not P. You take that statement first, then you negate it. And those are not necessarily going to be the same as what this is. So parentheses can absolutely change the logic behind the statement you're making because of order of operations, things like that. So there's a couple different ways of making the if P then Q statement. It's a couple ways. And some of these are obvious, some of these aren't. If P then Q is the basic one, but Q if P. Even though the P is taking place second, the Q is taking place first, that's still the statement if P then Q. And that's a little bit confusing, but it's because, look, you're still saying that P is the if part. Just because you wrote it second doesn't matter. A weird one that you may not consider, P is sufficient for Q. That's saying that that's saying that the truth of P is sufficient to establish the truth of Q. If P is true, then Q is true, because P sufficiently supports Q, basically. But the other way around, Q is necessary for P. Even though Q is coming first, that's still the if P then Q statement. A little bit confusing. But think about it. Q is necessary for P because what that means is that for the P statement to be true, whenever P is true, Q is also true. Thus, if you're trying to determine if P is a true statement, you can also look at Q. And if Q is a true statement, then you at least, or rather you can say that Q is forced to be true for P to be true. It's kind of weird, but being a male is necessary for being a father. Well, you can argue that. You can use only if, which is really weird. P only if Q. And then you can also just flip-flop around and say only if Q do you have P. All of these, while they might look different, while they might flip around the order you're reading them in, logically translate to if P then Q. P pointing towards Q. This might be one you kind of have to memorize at first. When you say P is sufficient for Q, you're writing it in the same order as the logical statement. But when you say Q is necessary for P, you're flip-flopping from the order of the original symbolic statement, but you're still correct. It's still that. So kind of a strange one. You can also have what are called if and only if statements. Those are called biconditional statements. What they actually mean is that not only is P pointing towards Q, not only if P then Q, but also the other way around, if Q then P. Kind of an interesting idea. So the way we symbolize that is we have a double arrow. Not only is P pointing to Q, not only is it if P then Q, but Q is also pointing right back at P. So if Q then P. And that means if and only if. Kind of a weird concept. It's called a biconditional because it's conditional and it goes two ways. Bi means two. So kind of an interesting concept. And so there's a couple ways that you can say it. P if and only if Q. That's the biconditional. Q if and only if P. If P then Q, and if Q then P. And that one seems really weird. Let's look at it in more detail. That one seems awfully strange. But it's actually pretty cool because you can write this statement out logically. If P then Q, so P, I'll just use that for an arrow. P then Q, if P then Q. And if Q then P. But now let's use our logical symbols. We know that and can be an upside down V. How would I symbolize that? That's about as good as it's going to get. And we would put this statement in parentheses so that the order of operations is clear. If P then Q, and also if Q then P. But that's just equivalent to saying P if and only if Q. A two-way arrow. That's what it really means to make or to be the biconditional statement. This is actually kind of important that we really understand this one, especially. We use the if and only if statement all the time in mathematics. You can also say then P is both necessary and sufficient for Q, or Q is necessary and sufficient for P. There's all kinds of different ways to write it. So if and only if is a biconditional, it's two-way. A nice summary here of everything is this little box. You got the negation, which is a tilde before your statement, your logical statement. You've got the upside down V, that's the conjunction. P and Q, also P but Q if you wanted to say it that way. You have the disjunction, P or Q. You have the conditional, if P then Q. You have the biconditional, P if and only if Q. We will deal some more examples after we take a quick break here. Back to our PowerPoint screen. These were some of our potential statements: the negation with the tilde, the and statement, the upside down V, the regular V for or, the disjunction. Conditional is one arrow pointing, or one statement pointing to the other with an arrow. Bicondition is a double arrow. So really, so far, all we're doing, we're not actually assessing the validity of any of these statements. I can make false statements as long as I'm symbolizing them properly. That's all we care about right now. It doesn't matter. You could say Shakespeare is the king of the world today, which is clearly not true. But all I care about is, can you symbolize it properly, at least in this section. The next section that we're going to start today we'll actually introduce truth tables, and truth tables are where we can really see some of this logic shine. So let's be careful. Notice the use of parentheses. Parentheses are incredibly important to determine the order of operations. So let's start with two basic statements, P and Q. If P is the statement, she is wealthy. Who's she? It doesn't matter. It's just a statement. Q is the statement, she is happy. Well, if I had not, but then I put parentheses around the P and Q portion, we could read that logically as not P and Q. And what that translates to is actually the parentheses mean that the and goes first. P and Q, they're being conjuncted first, then we're negating the entirety of P and Q, simply because of order of operations. So really what that is, I'm even going to change the wording here. It is not the case. Can I change the wording? It doesn't want to let me change the wording. Okay. It is not true that she is wealthy and happy. So sometimes it's best to use like commas and stuff. Of course, for some reason, this doesn't want me to use commas. But what you're saying is that the statement she is happy and wealthy is itself false. Now down here, notice the subtlety. There's no parentheses around the P and Q part. So if I just read this statement logically in the logical form, I would still say not P and Q. Over here, I also said not P and Q. Either one, I would read this not P and Q. I would also read this second one, not P and Q. Oh my gosh, can't spell today. But they're not the same thing. So this is where you have to be very careful. When I say this one here, I would say not, and then I'd take a nice little pause. I'd take a little verbal pause. Not P and Q. Down here, I would say not P, so it's clear that the not goes with the P. I'd say not P and Q. This means she is not wealthy. Also, she's happy. She is not wealthy, but she's happy, which is possible. There are people who aren't wealthy who are happy. Don't believe that great American lie that you have to be flowing around in money to be happy. You can be happy at any stage of your life, whether you're in school and you're a broke college student, which I've been there and it's not fun being a broke college student. You can still be happy and be a broke college student, I promise you. Now, I'm not saying your life's going to be cherries if you can't, pay your bills and stuff. That is not fun. But I think there are still, you can still find enjoyment in things. Look, Halloween's coming up. Halloween is like a little bit over a week from now. And Halloween and Thanksgiving and Christmas, those are just the best times of the year. So even if you've got bad things going on in your life, and I think all of us have at least something, I do think you can find optimism in a lot of ways, which has nothing to do with our lesson here, but whatever. Then we have the statement not, and then in parentheses, P or Q. So we're negating the entire P or Q statement. It is not the case that she is wealthy or happy. It is not true that she is either wealthy or happy. That's kind of logically equivalent ways of expressing that. So now things can start to get really, really ugly. Things can start to get really ugly, and you can bring P's, Q's, and R's. You can have nots flowing around, ands flowing around, if-then statements flowing around. And, it creates something that's just not going to be a whole lot of fun if we're being honest. So what we'd say is this statement is Q and not, if Q and not P, then not R. Notice the comma kind of helps split up the thoughts. We would take this statement, Q and not P, we would take it at once. We put in parentheses to say that it's grouped, and then the not R is the if-then part. So also, even within this substatement, you have to know that the tilde immediately goes with the P. You can re-parenthesize these things and create completely different logical statements out of them. And that makes life a little bit complicated, which is why we need to be very careful that we dot our I's, cross our T's. Look at this nasty business. Q and not, if not P, then not R. So we put like a comma. Even if a comma doesn't make a whole lot of sense in English, it's still rather helpful for keeping our ideas kind of organized together. So if there are parentheses, you're in luck because the parentheses tell you what to link together. So let's say we took three statements, P, Q, and R, and these are simple statements because these statements by themselves don't have any other connectives inside of them. And, or, if, then, if and only if, there's no connectives within each of these statements. We can use connectives to connect the statements together, but P by itself is a simple statement. So let's let P be the statement, a student misses lecture. Q be the statement, a student studies. R be the statement, a student fails. If you've ever watched Game of Thrones and you remember the character Jaqen H'ghar, I don't know, maybe you have, maybe you don't. It only ended last year, so you can't accuse me of being old and watching old TV. If you remember Jaqen H'ghar, he was some kind of assassin character, and he would talk like that. A student misses lecture. A student studies. It was kind of weird, but maybe you remember that, maybe you don't. Anywho, if you had this statement, Q and not P in parentheses, this is the statement if Q and not P, then not R. Which, using the P, Q, and R we put up there, it means if a student studies and a student doesn't miss lecture, then the student will not fail. That's exactly how we'd say that in English. So it looks rather cumbersome, but you just have to realize where the parentheses should go. They're usually, if they're not provided for you, you're going to have to use something called the dominance of connectives to know what goes with what. And dominance of connectives is an awful lot like our order of operations that we do in if you're just dealing with numbers and stuff, if you remember. Same three statements, P, Q, and R. If you had the statement Q and if not P, then not R. Notice the parentheses. The comma is great because it separates the larger statements that are meant to be taken separately. So Q and if not P, then R would literally translates to a student studies, and if a student doesn't miss lecture, the student ain't going to fail. That's what that means there. But if I were to just switch around these parentheses where they go, I could create a completely different logical statement. And so it's a little bit funky. Again, I've already gone off on a couple tangents in logic here, and I'm tempted to go off on another one, simply because this is the most interesting stuff that ever in math. You know, look, us having to multiply, add, subtract fractions, that stuff is kind of tedious. It's kind of difficult. But it's also stuff we've probably either seen a lot or, you know, especially fractions. The fractions are just a pain in the butt. Am I right? Am I lying when I say that fractions are a giant pain? No, even I don't care for fractions. I know how to deal with them. But if I have to work a problem with fractions, I'm going to look at that and go, how can I get rid of the fractions here? So I understand fractions aren't fun, but this stuff is fun. It's logic. We can take actual English statements, translate them, and evaluate their validity in the next section here. That's fun to me. That feels like it hits home more. Another thing, one last tangent, and because I just love this stuff so much, guys. Please indulge me. Please indulge me. I really, really, really think that logic is important. One thing that people have a misconception about, they would say, I'm such a logical thinker. And they think that that means that they're just smart or they study a lot. Or even worse, they think that logic is to just remove emotion. If you remember Spock from Star Trek, And that's just, I don't have any more modern example than that. If you don't know who Spock is from Star Trek, well, that's because that's a show from the 60s, and I don't expect you to know that. But Spock was a Vulcan, and Vulcans prided themselves on logic. And I feel all too often they associated logic with just not being emotional. That's not at all what logic is. You can be unemotional and not know any of this logic business here. You can have zero emotion about something and still make horrible, illogical arguments because you don't actually know what logic is. Logic is nothing more than a system of evaluating truth and arguments in this case. It's not just, I'm not emotional. Also, another thing that people who study logic all too often get wrong, they don't realize there is a time and a place for an emotional argument. If your argument works, if you can, jump up and down at the store when you're a kid to get, your, they used to call them shock tarts. Now they're, what do they call them? Like sours, or I don't remember. They changed all the names of my favorite candies and they got rid of them. You can jump up and down and cry to your parents to give you this candy. You just made an emotional argument. That's all they did. They're probably just sick of you and are like, whatever, just give them some stupid little candy if it'll shut them up. That an emotional argument can still work. It's not logical. Me wanting candy is not a logical argument, but it still works. So don't think that logic is the only thing that matters in this world. Absolutely not. Emotion is probably more important than that. But it is just interesting to know. We have something called a dominance of connectives. We have a dominance of connectives that tells us, well, hey, what if we didn't have parentheses around things? What if we didn't have parentheses around things? Could we still determine the order of how things should go? Where the comma should go, if we're trying to say this or that in English? Well, yeah, we're going to go ahead, just like we have an order of operations. The dominance of connectives is an exact analog to the order of operations if you're just dealing with numbers and algebra. So a dominance of connectives, the least dominant connective is actually the negation. And what it means is it's actually, when you're talking about dominance of connectives, you're talking about when does something become applied. The negation is the least dominant, which actually means it's immediately applied. Unless you have parentheses around it, the negation only goes to the next most immediate statement, P, Q, R, S, whatever. It goes directly with it and then does not apply beyond that. That's why it's the least dominant, because it burns out immediately. The next level of dominance is conjunction disjunction. Those apply a little bit further, but they only apply as far until you hit a conditional. Then they stop applying to the rest of the statement. And then the conditional is only as dominant as it's not more dominant than the biconditional. The biconditional is the big cheese. That's the one that really splits up statements into like a before and after this kind of thing. So interesting stuff. Let's see kind of how this applies. Look at this statement. Look at this statement. Well, look, there's an if-then arrow in there. There's the and conjunction. There's a negation in there. How do we know how to group things? How do we know how to group things properly? We use the dominance of connectives. The most dominant connective, there's no biconditional, there's no two-way arrow, which is the most dominant. So the next most dominant is just the single directional arrow, like this. This is gonna be what draws the line in the sand, if you will. Remember the old story of at the Alamo, they drew a line in the sand and everybody who wanted to stay and fight was allowed to stay and fight? This is the line in the sand. This means that there's one whole statement here, P, and then everything else is on the other side of it. And thus the parentheses go around everything after the arrow. This P doesn't need parentheses because it's just by itself. So it's kind of interesting. Look at this jumbled mess. Look at this jumbled mess. Look at this and this and this. It gets really ugly really quickly. These are just jumbled messes. Is it the statement P and all this crap? Or is it the statement P and Q, then this crap? It's the latter case. Because the most dominant statement is the single conditional. So we draw the line in the sand. Everything else is on this side, everything else is on that side. So we would put parentheses around the P and Q. And so on and so forth. Here, the biconditional is the most dominant. There's a conditional in there, but that's okay. So this is the line in the sand, is the biconditional. And then everything else before it is parenthesized. Everything else after it is taken as one statement. And then something like this is actually ambiguous. So it's not perfect. And this is because P and Q or R, that's very poor grammar, if you will, logical grammar, because the conjunction and disjunction are equal levels of dominant. So there's no telling, do I put parentheses around the P and Q, or do I put parentheses around the Q or R? There's no telling. I can't tell you because the and, the or are equally dominant, and there's nothing. So this is actually just this would probably, if you had no other way to deal with it, you'd probably read it from left to right. Do P and Q first, then do the or R with it. So let's see, P, Q, and R. We're back to the statements. P, I fail the course. Q, I study hard. R, I pass the final. Those are going to be our three statements. If we had the statement, I do not fail the course, if and only if I study hard and I pass the final. Well, we see the if and only if embedded in there. That's a biconditional, so that's going to be the most dominant part. So you put that double arrow down there. Everything that came before it is its own thing. I do not fail the course. Well, that's not P. That's the opposite of P. If and only if I study hard and I pass the final, that's Q and R, and they are taken to be in parentheses. So kind of interesting. So if all I say is, I do not fail the course, if and only if I study hard and I pass the final. Who the heck knows how I group those things? Unless you knew about dominance of connectives, you would just write it out with no parentheses and have no idea where to group things. I do not fail the course if and only if I study hard, comma, and I pass the final. So this one's actually kind of interesting because the comma separates the two ideas. And thus, the actual dominant one is going to be the and in this rare case because a comma here forced this first part to be in parentheses and this second part to be its own thing. So dominance of connectives only kicks in if there's nothing else, no other thing to tell you, if nothing else tells you what to do. But actually with the way it's written, this first part gets in parentheses. So this is no longer the most dominant connective because there was no ambiguity. Up here, there was ambiguity if I did not know my dominance of connectives. Take the statement, I do not fail the course if and only if I study hard and I pass the final. Because there's no commas, there's no parenthesizing for us already, which just means that we don't have any guidance. We have to use dominance of connectives. So I see the if and only if, that's going to be the dominant connective. I do not fail the course comes before it, that's not P. I study hard and I pass the final comes after it, that's Q and R. Thus, I would put parentheses around the Q and R. Like that, and then the not P is taken on its own. You don't even technically need parentheses there. That's what that means. So once again, I'll reiterate, we have not even talked about assessing the truth of any of these. I do not fail the course if and only if I study hard and I pass the final. That could actually be nonsense. You could study hard, you could pass the final, but still not do well enough based on your other exams and all the other things, and you could still end up failing the course. So we have not actually said if any of these statements, even these major compound statements, are true or false. All we're doing is rewriting them. We're rewriting them symbolically using our logical connectives, using our symbols. That's it. We are not going to assess the truth of them until now. Let me pull up our last set of notes. So let's move on. We're going to now look at the last section of chapter 3 here. We're going to look at the last section. And now we're going to really get into the power of all this. We are going to look at something called truth tables. Truth tables. Now, this thing didn't even give you the epic introduction to truth tables. The epic introduction is this. A truth table allows you to look at every possible outcome. It allows you to look at every possible outcome and then creating logical statements using connectives and all that out of it. You can then find the truth value of a statement. This is what we want. This is what we're getting at. This is where we make arguments. So for instance, let's look at a regular old statement P. P could be any statement. Shakespeare wrote Hamlet. Joshua Gunther, your professor, is the coolest guy in the world. That one's probably, that one's dubious. But P could be any statement you're starting with. What you do in a truth table, you take your statements, your elementary statements, and you write out all their possible states. So for instance, if you just have a single statement P, it's either true or false. We defined that from day one, which was actually just last class. We defined that as we said that's the definition of a statement. It's something that can either be true or false. Well, we can then create the truth table for the negation, the not P statement. We can take that. In the case that P is true, not P is false. So you read along a row here. In the case that P is true, the negation is false. In the case that you start with a false statement, the negation then becomes true. That's what a truth table does. So all you're doing is evaluating each of the possible combinations of things for your statements that you're starting out with, and then finding out the truth of compound statements you're forming from them. Take it to the next step. So the negation is exactly what it sounds like. It just changes the truth values. The conjunction. Well, in order to conjunct, we need to have two different elementary statements we're starting with. We have the statement P and we have the statement Q. Now let's completely ignore that third column for just a moment. You, my friend, are shunned. Oh, it didn't happen. There it is. Let's ignore that third column for just a moment. Let's have a little chat about this. Let's say you have two statements, P and Q. They could be anything. P could be the statement, Shakespeare is the nicest guy in the world. Q could be the statement that I have thrown a chair across the room in my life. That's not true, but I'm just saying that's a possible statement. What we're going to do is we're going to take every combination of those two statements being true or false. And there's four. The first statement could be true and the second statement could be true. Then what we do is we analyze what all these other compound statements, what they mean based on this. The first statement could be true, the second statement could be false. The next possibility, the first statement could be false, but the second statement could be true. The final possibility is that both statements are false. So you agree that there's only four possible combinations here. Earlier, when we just had a single statement, P, there were only two possibilities. Either P is true or false. But when we bring another statement into the mix, we have to look at every combination of the two of them being true or false. If we were to add a third statement R into the mix, we'd actually then have 8. We'd have 8 possible rows. If we had another statement, even S, we'd have 16 possible rows. In fact, that sounds an awful lot like the number of subsets of something. Remember, we said it was 2 to the power of however many sets or elements you had in the set. But let's not get ahead of ourselves. So the conjunction basically is saying this. Let's erase it. Where'd my annotate go? This is saying this. When P is true and Q is true, the statement P and Q is also true. That's what this row literally means. When P is true and Q is true, P and Q is true. That's what this row means here. And it's kind of sloppy. Maybe if I did used a little magic, I think I can make it better. That's what this first row is saying. When P is true and Q is true, the statement P and Q is true. Let's look at just some other row. How about this row down here? When P is false and Q is true, the statement P and Q is false. Let me give you an example of that. Let's use actual statements. So I kind of talked about this last time, but let's say you're going to a bar. Now, I'm sure no college students go to bars. I have certainly never been to one myself. Certainly not since March, but anywho, let's say you're at a bar. You're at a bar that has a band playing tonight. They have a band or a DJ or something. Now, most of the time, the bar doesn't pay the band out of their own pocket. What the bar does is they say, well, if you're going to bring in a good sized crowd, if you're a popular enough band or you tell enough of your friends, we're going to charge a cover so that the more people who show up, we'll give you the cover. So we might charge a $10 cover for a person to get into the bar tonight. But let's say that bar also has a rule that you have to be at least 21 to get in. So you're at a bar that has a band playing tonight. The bar is charging a cover of, I don't know, 10 bucks. The bar also requires you to be 21 and up to get into the bar in the first place. Notice also means the word and. So let's turn this into a little bit of logic. Let's say P is the statement, you have $10 and it's implied $10 you're willing to part with. You're willing to pay the cover. So maybe let's just call it that. You're willing to pay the cover. You're willing to pay the cover and get into the bar. Q is the statement, you are 21 plus. The bar requires you to pay the cover and be 21 plus. So this is a perfect case of the and situation. And we can make a little truth table out of it. Sure, I'll construct one with you. Here's P, here's Q. I'll make a table with you, sure. Now let's think logically. There's 4 possibilities. P and Q. There's 4 possibilities. Let's say you're a person who's considering going to the bar. There's 4 possibilities. The first one is that you're willing to pay the cover. The second one is that you're at least 21. So that's this row here. You're willing to pay the cover and you're 21 plus. Is the bar going to let you in? If you're willing to pay and you're at least 21, you've followed their rules. So P and Q is true here. So in this context, P and Q means the bar will let you in because you are both willing to pay and at least 21. Now let's think of someone else. Let's say you're a young rascal. Let's say you're 19 years old. Some of you out there might be 18, 19. You're not getting into bars, and there's no way for you to get around that. There's absolutely no way you could get into a bar if you're under 21. So don't even think about it. Let's say it's the case that you would be willing to pay the cover, but you're not at least 21. You're a rascal. You're 18, you're 19, you're 20. Is the bar going to let you in? No. Assuming you show them the correct ID, they will not let you in. Let's just address it. If you try to have a fake ID, they're probably going to spot it and they are going to kick you out. So I kind of have to say that, but yeah, don't try to get into a bar with a fake ID, you goobers. So in this row, you're saying you're willing to pay the cover, but you're not at least 21. Q is false. So it's false that the bar is going to let you in. Here, you may be unwilling to pay the cover, even though you're 21 plus. You're just like, no, I don't feel like paying 10 bucks. You could be 25. Are you getting in the bar? No, unless you try to sneak in through the back, no. And then if you're both unwilling to pay the cover, and also under 21, is the bar going to let you in? No. So that's why this truth table makes sense. When you're saying and, you are saying the hardest thing, the most difficult thing. You have to both check the first box and the second box for this entire thing to be true. If you only check one box or neither of the boxes, it's not going to happen. Now, let's say this bar is a little bit cooler, or maybe not cooler, but the bar has a weird rule. There's still a band playing. A bar is in the business of making money, nothing else. So there's still a band playing. The bar will let you in if you pay a cover or if you're 21 and up. That's a pretty common situation. Because if you're 18, some bars, you're allowed to get into a bar when you're only 18, 19 years old. There are bars that are like that. Usually they're also restaurants and they just serve drinks too. Most restaurants serve drinks as well. So bars are like, yeah, why can't we let 18-year-olds in? Well, a lot of them don't because you can't legally drink. They're not allowed to serve you alcohol. So they're still not going to serve you even though you can get into the bar. But they'll let you in if you just pay the $10 cover. If you are over 21, they're not going to charge you a cover. How come they're not going to charge you a cover? Because you're old enough to buy drinks and they think they're going to make their money off you from selling you drinks. So now this bar has a different policy. This bar you don't have to be both of these things. You do not have to be willing to pay the cover and be 21 plus. You just have to pay the cover or be 21 plus. As long as you do at least one of those two things, you can get in the bar. So now this last one, let's just create the truth table for the or statement. P or Q. Let me use black. So this bar is a lot less, they're a lot more willing to let you in. They're not as tight with their rules. So in this bar, if you are both willing to pay the cover and you're 21 plus, will they let you in? Yeah, they're not going to turn you away. You don't have to pay the cover. But if you just want to go hand $10 to the bouncer or the register person, they might say, okay, have at it. So if you're both those things, they'll definitely let you in. But here, you're willing to pay the cover, but you're not quite 21. Is this bar going to let you in? This one will. So the or statement only requires that at least one of the statements it's constructed from be true. Down here, you're not willing to pay the cover, but you're at least 21, the bar will let you in. Even if you don't end up buying any drinks, they're assuming you're going to buy some drinks. The only way they won't let you in is if you won't pay the cover and you're not at least 21. Then that's false. So the or statement just requires at least one of the statements it's constructed from to be true. But if both are false, the or statement is also false. Okay,